Have you? Alkali, base. There are various definitions, but let's understand it very simply right now. Anything that produces H plus, anything that produces O minus, generally speaking, okay? So examples could be HCl, HNO3, H2SO4, H3PO3, things like that. H3PO4, whatever. Bases, NaOH, MgOH, aluminium. Aluminium is a little funky. Let's put it here. What else? Calcium. Okay. KOH. Must have heard about these things, right? These are bases. These are acids. These are coming from the metals. These are coming from the nonmetals. So generally, metallic oxides and metallic hydroxides behave as bases. And non-metallic oxides and non-metallic hydroxides, do they exist? I mean, they will not. Why? Because a hydroxide is OH minus, and if you have a non-metal, which is F minus or Cl minus, this will not generally come in together, generally. So let's only think about the oxides in here. So NaOH, how is NaOH forming? So you take a sodium oxide, dissolve it in water, and you get NaOH plus H2. So this is a basic oxide because a basic oxide is dissolving in water to give a base. So that's basically a basic oxide. An acidic oxide is the other thing. The acidic oxide is just anything like SO3, H2O, H2SO4. So you find all these metallic oxides on the left-hand side, all the base-producing things on the left-hand side, and all the acid-producing things on the right-hand side. And somewhere in the middle, you'll have both. So things like this, we call it, they have an amphoteric nature, amphoteric oxides. They can behave as both acids and base. And by that I mean, they can react with both acids and bases. It's not exactly what I'm trying to get into. This is a big study in itself. So that's why I'm not going that way. But if anyone has any if anyone is interested, I can talk to them personally. But my idea is to connect in your heads the idea about the sizes that are decreasing. Since the sizes are decreasing, it's becoming more and more hard to pull out the electrons, and that is why the ionization enthalpy is increasing. Since the ionization enthalpy is increasing, it is becoming more and more difficult to form the cations. Metals generally form cations, and that is why the metallic nature is decreasing, metallic nature is increasing top to bottom. Does that make sense? The non-metallic things should just follow the opposite trend, generally speaking, right? But we'll see. So does that make sense? Your homework is to find out or the ionization enthalpy should increase this way, right? This is period 2. Should increase like this way. But my question is, the ionization enthalpy of nitrogen is greater than oxygen. My question is why? Think about this while I erase this part. This should be the opposite, but it's not. Nitrogen's ionization enthalpy is more than the ionization enthalpy of oxygen, and the question is why? Okay, we'll discuss this in the next class. You'll have to write the electronic configuration. But let's move on to electron affinity. Okay. Electron affinity is kind of like the opposite of ionization enthalpy. So electron affinity is the amount of energy released, and what will be the delta H? Positive or negative? Positive or negative?
Energy released. Did you say energy released?
Energy released, exothermic. Sorry, yeah. It's negative. Ionization enthalpy was positive. This is negative. The amount of energy released when an atom accepts an electron to form an anion. It's just kind of like the opposite. Okay. Now, electron affinity also depends on the size, and basically on the size, and the size depends on the nuclear charge and the number of orbits. It has similar behavior. So whatever trend was happening with ionization enthalpy is a similar trend, right? So the electron affinity also increases from left to right and decreases from top to bottom. So the process is opposite, the energy is released. So the trend remains the same, right? This also gives you an idea about, so the most electron, the energies, the elements that will have the most electron affinities are going to be metals or non-metals, or which side of the periodic table will they be on? Towards the right. This is the opposite, right? So the things with the most electron affinity are on the right, same as the ionization enthalpy. Electron affinity is also on the right, but this behavior somewhat resonates well with the non-metals. Now see this example and see this example. Which do you think is easier or more likely to happen? The Cl is more likely to happen. Why? Because this is very stable. That is why. This reaction is more likely to happen because the product of this reaction is more stable than its reactants. So this is more likely. This is less likely. The other thing was more likely, the ionization enthalpy. That was more likely for this because that way sodium was getting stabilized. Here, this is more likely than that. Therefore, if this is the more stable, then the amount of energy released will be more in which one? This or this? When you release more energy, does that mean getting to more stable? Right. So if this is becoming more stable, then shouldn't this release more energy? And does the trend match? Because we said that the electron affinity, which is the amount of energy released, will increase from left to right. That means more energy will be released when you come towards the right. And why more energy is released when you come to the right? Because you're getting more and more stable products. You have to go and watch this video, this section again to make sense, because this is a very profound understanding in my small world. Because when you become more stable, more energy is getting released, and this is what basically is electron affinity, is more and more energy is getting out. Right? It should all make sense in your head, not on paper, not in your. Sit down and think and compare ionization enthalpy, electron affinity, energy released. It's just the opposite, but everything should fit in your brain. Okay? Yes?
I was going to say, if it helps, one of the ways that I think of the kind of less energy, more stable thing is like with a puzzle. And you can imagine if you have a puzzle with like 500 pieces, it's going to take a lot more energy to put all those together and to make it the kind of more stable configuration than it would to just destroy it and pull all those pieces apart, i.e. the like higher energy.
Yeah, I think like kids have more energy and therefore they are more unstable.
That's a good one.
It's very unstable, and as you grow old, you're becoming more and more stable. It's not always true, but I mean, most of it. Okay, now, if you get the first electron, this is negative. So this is delta H is negative for electron affinity 1. What do you think the delta H is? Positive or negative?
Positive.
Why? You're right. Ionization enthalpy, you're taking out one electron, energy, you have to invest some energy. You're taking out the second, you have to invest more energy. So both of them are positive. Both of them, both IE1 and IE2 are endothermic processes. But electron affinity 1 is an exothermic process, delta H negative, but electron affinity 2 is an endothermic process. Why?
Because he's already stable, and you have to the energy.
And it's not just stable, it's negative, and you're putting more negative into it. Right? So if it's negative, you're putting more negative, it becomes harder. So EA2 is endothermic, EA1 is exothermic. Right? Make sense? Okay. Next class, we will wrap up periodic properties and go into geochemical classification. And all the others, so there is this electron affinity, which is just which also follows similar trend as this, but we'll discuss a little bit and then move on to the classifications and then and bonding. Thank you.